Hi, everybody. I'm Denny Dahl from IonQ, and I'm going to present the solution to the third challenge problem, which is a four-city traveling salesman problem, or TSP. We'll analyze the problem using two different encoding schemes and build QAOA circuits for both encodings. We'll determine some characteristics of the circuits and then tune the variational parameters in the circuits to maximize the probability that the circuit returns the TSP solution with the shortest distance. We'll place a bound on the number of C0 gates we allow in these circuits. This bound is approximately what we can hope for with today's NISC hardware. With cities A, B, C, and D, we have six legs, each of which connects a pair of cities. We'll denote the leg variables using an X with two subscripts, one for each of the two cities on the ends of the leg. The four cities and their pairwise distances are shown here on the lower left. The distance portion of the objective, as printed out by my Python program, and the penalty portion of the objective are shown on the right. The total objective, which is not shown here, is the sum of the distance and the penalty function, after scaling the penalty by lambda. To do the first exercise, we'll need to evaluate the total objective for all 64 states which result from assigning 0, 1 values to the six leg variables in all possible ways. Of these 64 states, exactly three are valid, and these correspond to the three valid tours. The other 61 states are invalid because they fail to form a four cycle of the cities. We can label the 64 states using binary integers 0 through 63, where the six leg variables correspond to successive powers of 2 in the binary integer. The ordering of the leg variables must correspond to the successive powers of 2 in the binary integer. With this correspondence, the three valid states are 45, 51, and 30. These three states correspond to the three valid tours with lengths 5, 6, and 7. On this slide, we try three values for lambda, 1, 2, and 3. In the top box on the left, lambda is equal to 1. The box lists all the states that have objective value 5, 6, and 7. The requirement we must satisfy is that the objective value for all the valid tours is strictly less than the objective value for all the invalid tours. In this case, we see that there are multiple states with objective value 5, 6, and 7, but we know that there should only be one valid tour with each of these lengths. We conclude that lambda is not large enough. In the middle box, we try lambda equal to 2. Things look better here. The tours of length 5 and 6 appear by themselves, which is good. But the tour of length 7 appears with two additional states with the same objective value. Thus, lambda is still not big enough. In the bottom box on the left, we've taken lambda to equal 3. In this case, the states with objectives 5, 6, and 7 appear by themselves. All other tours have higher energies. Thus, 3 is the smallest value of lambda in which all invalid states have higher objective than the valid states. Building the switch network objective is easiest if you use a symbolic algebra package like SymPy. I took a completely manual approach and wrote out the expressions for all 16 indicator functions explicitly. On the left, you can see four of the 16 indicator functions. Indicator tau AE is a function of the six switch variables, which are assembled into a list of length 6. Input port A is routed to output port E if switches X0, X2, and X4 are all turned off, or if X0 and X4 are turned on and X3 is turned off. Similar logic applies to each of the indicator functions. Now that we have all 16 indicator functions, we can assemble the distance objective. Two of the six terms in the distance objective are shown here on the right. The distance from city A to city B is counted in the objective if the switch network routes cities A and B to adjacent output ports. There are 8 ways that can happen, and they are represented by the 8 terms that make up the leg AB variable. The first of the 8 terms turns on when input port A is routed to output port E, and input port B is routed to output port F. Since A and B are now adjacent at the output, the tour will go from city A to B, and so we must include the distance between these two cities in the objective. The other 7 terms in leg AB correspond to all the ways that input port A can end up adjacent to input port B once both are mapped to the output. Similar repetitive logic can determine when we need to include leg AC in the distance objective. Likewise for the other 4 legs, which are not shown on this slide. This is the result of computing the distance objective. Since there are 6 switch variables, each of which may or may not appear in a term, the maximum number of terms is 64. Of the 64 possible terms, only 48 appear, and the number of terms of each degree is shown in the table in the lower right. As we evaluate the distance objective for each possible setting of the 6 switch variables, we will always get a valid tour. The number of tours of each possible length is shown in the table in the lower left. The final exercise requires us to build the QAOA circuits for the leg variable and the switch variable encoding. Here is a P=1 QAOA circuit for the leg variable encoding. The circuit begins with Hadamard gates for each qubit. Following this initial layer is the exponentiated Hamiltonian. This is represented by the single qubit RZ gates and the RZ gates sandwiched between 2 C0 gates. Following the exponentiated Hamiltonian is the mixer operator, which appears as RX gates, 1 per qubit. The total number of C0 gates is 24, which is twice the number of quadratic terms in the Hamiltonian. This circuit contains a single layer of exponentiated Hamiltonian and mixer. If we increase P, which tells us how many layers are in the circuit, then everything we see here, with the exception of the Hadamard gates, gets replicated. If our total budget for C0 gates is 3,000, then dividing 3,000 by 24 gives us 125, the maximum number of layers we can include without exceeding the allowed number of 2-qubit gates. The QAOA circuit for the switch network at P=1 is shown here. The difference between this circuit and the circuit for the leg variable encoding is apparent. In this circuit, we see deeper ladders of C0 gates surrounding the single qubit RZ rotations. These deeper ladders correspond to the exponential of higher order terms in the Hamiltonian. A term of order n will require 2n minus 2 C0 gates in its ladders. Also note that there are opportunities for cancellation of C0 gates here. 3 such cancellations are shown. These are back-to-back pairs of C0 gates which use the same control and target qubits. The action of such a pair of C0 gates is equivalent to the identity, and so we can remove these pairs. This reduces the total number of C0 gates from the initial count of 34 down to 28, since we can remove 3 pairs of these gates. Dividing 28 into 3,000 gives 107, and so we can use up to 107 layers in our QAOA circuit. These 2 charts show the best results I was able to obtain with my 2 QAOA circuits. On the left is the leg variable circuit. Using 125 layers in the QAOA circuit and a linear ramp for the beta and gamma values, I saw 96.8% of the probability in the shortest tour, which had length 5. Most of the remaining probability, 2.9%, ended up in the next shortest tour, which had length 6. The rest of the states had negligible probability. This was with a value of 3 for lambda. The chart on the right shows the results for the switch network. In this case, I had to sum probability over the 24 different computational basis states that all correspond to a tour of length 5. In this case, the total probability for the circuit to produce the shortest tour was 99.6%, which is slightly better than the leg variable circuit. Most of the remaining probability, 0.3%, ended up in the tour with length 6. That's my solution to the challenge problem. I hope you enjoyed working on this problem and that you learned some new ideas about how to encode combinatorial optimization problems on quantum computers. Please feel free to send me email if you want to learn more about IonQ and our work with quantum computers. Thanks and goodbye.